Uh, Good morning, and thank you for giving us the opportunity to present our study titled The Robust Non-conforming Virtual Element Scheme for Time-Fractional Dissipative Wave Models on Polygonal Meshes. In this particular study, uh, we are thankful to the organizing committee of the CMMSE 2026 for giving us this opportunity. So we are going to go with the. My name is Zafar Madidar. I'm the assistant professor at the Department of Mathematics, School of Engineering, Dayanand Sagar University. We are going to the outline of this particular study. We are going to give the introduction and of the virtual element technique as well as the governing model, dissipative wave models, the fundamentals and the basic principles of the virtual element technique, and the motivation behind this study and the mathematical framework that will include the discrete schemes, the convergence analysis, well-posed results, and with the numerical validation over the different set of meshes like regular Voronoi and the non-convex meshes. We are going to validate our theory and our study, and we are going to conclude some results from this numerical experiments, and then we will have some references therein. Going to the introduction of this particular study, we first go with the virtual element technique, which is considered to be the generalization of the finite element method on polygonal and the polyhedral meshes in the two-dimensional and the three-dimensional spatial domains respectively. We know that it's independent of the particular shape when we are talking about the arbitrary polygons. The particular shapes like the structured meshes or the triangular meshes or the quadrilateral meshes. Herein we can take any arbitrary set of polygons, like we can take pentagons, we can take hexagons, we can take non-convex shapes, and so on and so forth. And the next important thing about the virtual element technique is that the basis functions are virtually constructed. That means they are not explicitly known to us. We are going to utilize some of the operators in order to make the bilinear products computable, and virtually we are not going to have the explicit definition of the basis functions. That's why the virtual element method. The virtual element method has some advantages, like with the less degrees of freedom, it is going to give us the good accuracy, the accuracy like other numerical methods, and this way the computational cost is also reduced. The virtual element takes consideration in the complex geometries because of the flexible mesh shapes, flexible elements, and it takes into consideration the disadvantage that we faced in the classical finite element methods, that is the hanging nodes. The hanging nodes can be included in any element geometry, and it can be formed as any arbitrary polygon or an arbitrary element. Just by knowing the or choosing the finite dimensional virtual element space and knowing the degrees of freedom, these two components are sufficient for us to implement the virtual element scheme for any governing or for any partial differential equation. Basically, the virtual element method has some advantage over the existing numerical methods, and it is relatively new, so we can utilize it for the different set of PDEs. Now, going to the fundamentals of VM, we have the first set, that is the degrees of freedom. For degrees of freedom, in a conforming virtual element method, we are going to choose the vertex values, we are going to choose the edge moments, or we are going to choose the internal moments. These are completely computable individual values that are going to be utilized in order to compute the solution of any of the PDEs with the choice of the finite dimensional virtual element spaces. In a non-conforming virtual element method, we are only going to consider the edge moments and the internal moments, not bothered with the vertex values. Then we have the weak derivatives and the projection operators. These projection operators will help us to make our bilinear forms computable. That means we are going to use the elliptic operator, we are going to use the L2 orthogonal operator in order to make the bilinear product corresponding to the diffusion, corresponding to the dissipation. We are going to make them computable bilinear forms. Then the choice of the local virtual element space that's going to be formed, wherein the local solution of any element or over any element lies by just with the continuous H1 continuous way, we are going to assemble them to form the global virtual element spaces. Now we need to have some regularity on these elements. We are going to have a regularity, the shape regularity, to maintain the stability of the elements. We are going to have this assumption that any of the edge should not vanish at any point of time. These are some of the assumptions that we are going to take for these elements, and the figure 2.1 illustrates the location of the degrees of freedom in a non-conforming virtual element method for different VM orders like k equals to 1, 2, 3, and 4 respectively. In this particular figure, we have the edge moments denoted by the red squares, and we have the internal moments given by the blue dots inside these hexagonal elements. Then we are going to the mathematical framework of this particular study. We are going to take a simple governing equation that is we have first we are going to define the motivations of this study. We are going to why do we choose the numerical methods such as virtual element method to study the dissipative wave equations. We know that the flexibility in the meshes and this will help us capture the non-ideal behavior or non-ideal wave attenuation with the complex terms like the fractional dissipation and all those. And in order to overcome the geometric and the computational limits of the structured meshes of any other finite difference on finite element schemes, we are going to choose the virtual element technique, and this was one more motivation in order to do this work with this particular area. And using this mesh discretization, a flexible mesh discretization, we can take any set of domain, we can take any set of complex partial differential equations, and we can move on, have a numerical study corresponding to these complex model equations. So these are few of the motivations that made us look into this particular area and choose the virtual element method as a relatively new numerical method for this particular study. Now, the equation 4.1 in this is the governing equation for a fractional dissipative wave equation, wherein we have a time derivative, second order time derivative. We have a fractional dissipation represented by the second term in this, and we have the spatial diffraction given in a space direction given by the Laplacian of the unknown potential u. And on the right hand side, we have the force term g of x comma to external force term. Now we have the coefficient nu, that is the damping coefficient, and which can be variable as the constant value, and the alpha, that will be the fractional order of a dissipation. Now in our study, we are going to take the Riemann-Livoli type fractional derivative in our mathematical model. We have Laplacian operator that represents the spatial diffraction. We have the external source term. We have a bounded polygonal domain in a second order domain, and with the partial of omega as a boundary. We have the initial and the boundary conditions given by the non-zero values. We are going to utilize these particular values in order to find the numerical solution of a given governing equation. With the complete theoretical analysis as well. We are going to form a fully discrete scheme using a virtual element method in space. We are going to use Newmark predictor corrector in time direction, and we are going to have the complete numerical solution with the given boundary or the initial conditions. The basic VM implementation here is, what we are going to do is, we are going to start with a problem domain, a simple problem domain, whichever it is, square domain or the circular domains or any other non-convex domains. We are going to discretize it in terms of arbitrary polygonal meshes. These can be regular meshes, these can be non-convex meshes, flexible in the virtual element technique. We are going to then go with the choice of the degrees of freedom in order to have the continuity, and then by just choosing the finite dimensional virtual element space, we can implement this particular scheme. Then when we have the variational form of a given governing equation, what we are going to do is, we are going to have the local bilinear products that are going to give us the solutions of over the local element. Any local element. It can be a regular Voronoi mesh, it can be a non-convex mesh, or it can be any structured or unstructured meshes. Then in the continuous way, we are going to assemble all these terms, all these local contributions for each term, for the dissipative term, for the time derivative term, for the diffraction term. and for the load term as well. We are going to assemble them and we are going to form a global solution. And we are going to solve this resultant system, which is going to be an algebraic system, either a non-linear algebraic system, either a linear algebraic system, depending on what in the governing model is. If we have the non-linear algebraic system, we are going to use the fixed point iteration techniques. We are going to use the Newton's method in order to find the solutions. If we have a linear algebraic systems, we can go with the direct methods, matrix multiplication, etc., in order to get the results of this algebraic system. Then by post-processing, we are going to extract the results, we are going to visualize the results, and what those results mean, we are going to compare it for the ideals as well as the non-ideal cases. This is the basic scheme of a VM implementation for this type of a model or for this type of a study. Now going to the we have in this study we are going to provide all the theoretical results which are going to be validated over a different set of meshes. We are going to choose the Voronoi meshes, we are going to choose the non-convex meshes for different examples. With this, we are going to have a simple variation or a weak form in equation 2. We have corresponding to each term of a governing model, a second order time derivative, a fractional dissipation, a spatial diffraction. We have a arbitrary shape function or a test function V that is in a Sobolev space of order 1, and we are going to integrate it over the domain omega. Now these integrals are not computable yet. Now by means of a projection operators, by using of an energy operator and the L2 operator, we are going to make these computable. And using the stabilization, we are going to have the consistent as well as the accuracy followed in these bilinear products. Now, as I said, we have two important aspects. That is, first is we are going to have a set of degrees of freedom. We are going to choose a finite dimensional virtual element space, and these two are enough for us to proceed and implement the scheme. Now we have defined a non-conforming virtual element space that takes into consideration all that lower order and the higher order derivative terms from the governing model. Then fully discrete scheme given by equation 4.2, wherein MH is a global discrete mass matrix. We have AH omega as a corresponding matrix to the dissipative term. We have KH, the stiffness matrix corresponding to the Laplacian term, and GH we have load term or the matrix representing the load term or the load contributions. Now theorem 1 explains the well-posedness of a fully discrete scheme that we have formed. We have a bound over a time step size delta t given by second equation in this particular statement. And by choosing the particular set of Newmark predictor parameters like beta equals to 0.2 and gamma equals to 0.5, we are going to get a second order convergence for the Newmark predictor, which is well established that the Newmark predictor character scheme is second order convergent with these Newmark parameters. So now we are going to focus on the in space direction using the virtual element technique. In the error estimates, in space direction, we already know it's well established for the Newmark predictor character scheme. For these set of parameters, we have second order convergence. Now we are going to prove that the fully discrete scheme satisfied this error bound or this convergence order, that is k plus 1. If for VM order k, we are going to get the second order convergence, k equals to 1, we are going to get second order. For k equals to 2, we are going to get third order convergence, whereas for the time scheme or the Newmark scheme, we are going to get the second order convergence with these parameters. And these are the theoretical proofs of attaining this order of the convergence k plus 1 in space direction and second order in time direction using this particular hybrid scheme, wherein we are using the virtual element method for space variables and we are going to use a Newmark predictor character scheme for the time variable. All these results are supported by the numerical simulations or the numerical experiments. First experiment will be run over the regular Voronoi meshes given in the subfigure A, and the other example or other numerical experiment will be conducted over the non-convex meshes given by subfigure B. So in the first example, we are going to study the wave propagation on a regular Voronoi meshes as sample was given. We are going to take a square domain. We are going to choose the predictor corrector parameters 1 by 4 and gamma 1 by 2, and here we have exponential decay as a load term. And these are the boundary conditions and the initial conditions given in order, and this initial conditions are 0, so the system starts with the rest. Now these results, figure 5.2, it represents a wavefront propagation when the dissipation order is non-ideal. That means when alpha equals to 0.5, we are going to have this set of a propagation, and in figure 5.3 it is for the ideal case when the dissipative order is alpha equals to 1. This is for the example over the regular Voronoi meshes, and the load term is the exponential decay term. We are also going to visualize the behavior of the virtual element technique of first order and second order from figure 5.4. We see that the virtual element method attains the convergence rates of k plus 1 order in L2 norm and k order in the H1 semi-norm. So we have for both first order and the second order schemes, we have the second order and the third order convergence respectively in both L2 and in L2 norm, and in the k order in the H1 norm, that is represented by figure 5.4. In the figure 5.5, we have different dissipative orders alpha 0.5 and alpha 1. We have the amplitude decay study of the displacement and the velocity. If you see at alpha equals to 0.5, the dissipation is slower as compared to when alpha equals to 1. So we can say that the dissipative order, lower dissipative orders will result in the lower amplitude decay, and the higher dissipative order will have a sharp decay in the amplitude. And from this discussion, we can see figures 5.2 and 5.3, where we visualize the wavefront propagation at different fractional orders, and in figure 5.4 we visualize that the optimal convergence is achieved. In L2 norm it is k plus 1th order, and in H1 semi norm it's kth order for different alpha values, alpha equal to 0.5 and alpha equals to 1 both. And then figure 5.5 demonstrated at the dissipation order 0.5, the wavefront retains relatively more energy. That means the dissipation is slower as compared to when alpha or the dissipative order is alpha equals to 1. That means there is a significant amplitude decay or the stronger damping effect with the higher dissipative orders. We have for the example 2, we have again chosen the load term to be an exponential decay term, and we are going to go with the non-convex polygonal meshes in order to have this study. Here we have load term at the exponential decay, we have the Dirichlet boundary conditions, we have the Newman boundary conditions corresponding to this, and the initial values as well that can be computed from the exact solution as well. Now here in this particular example we have studied, we have again the wavefront propagation with the different fractional orders. We are going to take alpha equals to 0.5. We are going to study from figure 5.6. We have the wavefront propagation at different time steps that will simulate the potential with the dissipative order 0.5, and figure 5.7 shows the wavefront propagation when the dissipative order is alpha equals to 1. Figure 5.8 represents the convergence rates and the error values for different alpha values when they for the VM orders 1 and 2, and it supports the theoretical results proved earlier. Figure 5.9 shows the displacement and amplitude decay. From the discussion you can see 5.6 and 5.7 illustrate the evolution of the wavefronts with different alpha values. Figure 5.8 represents the optimal convergence achieved in L2 norm as well as the semi-norm, and the figure 5.9 demonstrates the dissipation orders and the amplitude decay for different dissipative orders like alpha equal to 0.5, alpha equals to 0.1, alpha equals to 1. In alpha 0.5, the dissipation is slower, or at alpha equals to 1, the dissipation is sharper. So higher the dissipative order, the sharper the dissipation rate, or the sharper the amplitude decay of both velocity and the displacements. Now there are several applications of these type of studies, because these are the model equations that can be utilized in order to understand the sharp behavior of a dissipative waves. One example that we are currently working on is the epileptic seizure propagation. It means it's very sharp, it's a sharp wavefront propagation. Now, in conclusion, we have wave model, a robust wave model is there, which can take a non-ideal as well as the ideal values of dissipations. We have a numerical stability that is assured by the virtual element method. We are going to get the optimal convergence over the different set of meshes. We can take the regular Voronoi meshes, we can take non-convex polygonal meshes, and it can still maintain the optimal convergence rates. And the applicability in the biomedical phenomena such as the epileptic seizure propagation is one of the studies we are currently doing. So in future we are going to look more into these type of model equations, and particularly we are going to go with the application aspects of these studies, and this will help us to understand the seizure waves better, understand the epilepsy better, and it can help us to predict or help us to have a preventive measures corresponding to each of the patient that we are dealing with. So understanding any of these wave equations or any of these dissipative wave models, we are going to have a direct implications in the biomedical simulations or the biomedical phenomena, wherein we can model such things in terms of a sharper dissipative wave equations. And because this model is a robust model which takes into consideration different set of the dissipative orders, a non-ideal as well as ideal order of the dissipative equations. So it will be a more robust model for us to understand the different set of application, different set of phenomena, and we can predict or we can have a preventive measure corresponding to each particular individual that we are studying. We have several first we are going to acknowledge I'm going to acknowledge the contributions of the co-authors of this particular study. We have Dr. M. Chandru from the Department of Mathematics, School of Advanced Science, Vellore Institute of Technology. Author Ms. R. Mohana from the Department of Mathematics, School of Advanced Sciences, Vellore Institute of Technology, and the contributions from Dr. Dibyendu Adak from the Theoretical Division, Los Alamos National Laboratory, and we have Dr. Eugenio Ramos from the Indian Scientific Computing Group, University of Salamanca, Spain. I acknowledge their contributions in this study, all of these authors, and we thank again for this opportunity to present our work in this conference. There are few of the references that we have utilized throughout this presentation that are given here. The first work corresponding to the virtual element technique, the basic principles of virtual element method.